So today, getting started today, just a couple of initial housekeeping announcements. Welcome, of course, to our next Eastern Region Science Sharing webinar series this morning. As a heads up, this webinar is being recorded via Google Meet. So please kindly ask to keep webcams off, mics off during the course of the webinar this morning. At the conclusion, we will, of course, have time for Q&A. So jot them down throughout the course of the webinar, and then we can field them at the end. And of course, if there are questions going beyond, we can field them offline. I'm sure our presenter this morning, who is Dr. Jana Houser from the Ohio State University, would be happy to answer them. So first off, thank you to you, Dr. Houser, for being with us this morning. Her presentation titled this morning is Rapid Scan Mobile Radar Observations of Tornadogenesis, Warning and Forecasting Implications. And to introduce her this morning, so Dr. Houser is an associate professor of meteorology in the Department of Geography at the Ohio State University in Columbus, Ohio, where she teaches forecasting, mesoscale, and synoptic meteorology. She received a bachelor's degree in meteorology from Penn State University in 2004, a master's in 2008, and a PhD in 2013 in meteorology as well at the University of Oklahoma, where she studied under Dr. Howie Bluestein from 2005 to 2013. From 2013 to 2022, she was a faculty member at Ohio University until she joined OSU in fall of 2022. She's a recipient of multiple teaching, research, and mentoring awards. And Dr. Houser specializes in radar-based analysis of tornadoes and the supercell thunderstorms that commonly produce them by using state-of-the-art mobile radar observations. Her particular interests lie in studying the formation of tornadoes and how the rotation of a developing tornado evolves with time and with height. And she also takes time to study the interaction of tornadoes with the ground beneath and addressing the problem of how topography and land cover impact tornado intensity and path. And with that said, Dr. Houser, thank you so much for being with us this morning and sharing all of the insights. You had the floor, and welcome to the Eastern Region Science Sharing webinar series. The floor is yours.
Great, Jordan. Well, thank you so much. It's a pleasure and an honor to be here with you fine folks today, even though it is virtual. I love the opportunity to speak with NWS folks because you all are really the front. You're the interface of the weather community and the warning center. So just a couple quick acknowledgements here. NSF grant, a couple of names here. Howie furnished radar data for me, a couple of collaborators and additional students who had helped out with data collection, and also just a little shout out for a paper that was published that is very similar to some of the content that you're going to be seeing here in MWR. All right, so we are a community of scientists here, so I'm going to take a little bit of time to talk about tornadogenesis from a science perspective. So traditionally, there are two hypotheses that explain how rotation that is basically contributing to a nascent tornado, how it's forming with time and with height. There's a traditional descending or top-down hypothesis, which was originally garnished by Lance Leslie in the early 1970s, and kind of a little bit later with some original numerical modeling of tornadoes. And then it was corroborated by early Doppler radar observations that Roger Brown et al. Secured from the Union City tornado in Oklahoma back in the late 1970s. So historically, up through the 70s, 80s, 90s, and into, I'd say, kind of the first half of the 2010 or the 2000 decade, this is how we pictured tornadoes forming from supercells. And we attributed this to the mesocyclone process and basically a concentration of rotation, which I'll talk about here in a moment. And then the second process, which is commonly referred to as a non-descending process or a bottom-up process, has historically at least been associated with non-supercellular tornadoes, so basically land spouts. And in this process, things kind of either start from the ground up or converge simultaneously. So let's delve a little bit deeper into this top-down hypothesis. So this is based around the idea of what's referred to as the dynamic pipe effect. And somehow what happens is you generate this area of strong rotation at roughly mid-levels of the storm. So within the mid-level mesocyclone, somewhere roughly between about 2 and 5 kilometers above ground level. And for whatever reason, we get this intensification of rotation. And when we have intensifying localized rotation, that's going to dynamically induce low pressure perturbation. So once we have this low pressure perturbation, we're not particularly interested in what's happening above, although it is potentially important. What happens below is what we're more interested in. So we have low pressure perturbation that's going to cause an upward acceleration of air that's directed into that low. And if we have any kind of ambient broader scale rotation, that upward motion is going to promote convergence. And as air is converging, it's going to relocate that rotation closer to the center of the axis of rotation, which is going to then basically, conservation of angular momentum, things get pulled in, we're converging, we're intensifying the magnitude of the rotation there. And ultimately what happens is we create a scenario where we have stronger rotation at a lower height. That stronger rotation becomes balanced through the cyclostrophic balance, where the inward directed pressure gradient forces is balanced by the outward directed centrifugal force. And once that force balance is achieved, we are again inducing low pressure perturbation and drawing air upward. And this process happens at progressively lower and lower heights until eventually the rotation, or the concentrated rotation, hits the ground. And then you have this formal in-up scenario where you basically have a tornado, which is at some later time. Okay. So this process conventionally has been assigned a time scale of roughly 5 to 10 minutes. So hypothetically, it takes about 5 to 10 minutes to form a tornado using this process, which is actually kind of nice, because if we would see this area of intensifying rotation at mid-levels or sort of low to mid-levels, and we could potentially warn on that and have maybe 5 to 10 minutes of lead time. So that's kind of nice. All right, so the second hypothesis, this non-descending tornadogenesis hypothesis, was interestingly actually the first theory that described tornadogenesis, and it was based on laboratory wind chambers from the 1960s. And in this case, you basically had an updraft, and you had pre-existing swirling flow that was being fed into the updraft from the low levels. That updraft essentially pulled that rotation upward, and through a combination of advection as well as conservation of angular momentum, your rotation intensified and formed a tornado. So what I described there was actually sort of this option 2, where you have this concentration of rotation at the near surface or ground level, and then that gets moved upward. The second possibility for this is that you have general broad rotation that's not tornado strength through a modest depth of the lower troposphere, and for whatever reason you have mutual convergence, or convergence of the surface is enough to just kind of dominate an advection process, where almost simultaneously the entire column starts to converge together and rotate. So there's not really a temporal scenario where you're starting at the bottom and building upward with time, starting at the top, building downward with time, but rather everything's kind of being sucked together all at the same time, bringing together that broader rotation into a more narrow and confined vortex that then becomes the tornado. With this process, typically tornadogenesis occurs relatively rapidly. So we're talking about on the order of 60 seconds or so. And conventionally, we have associated this process with non-supercellular tornadoes like landspouts, and basically there's some kind of rotation that's induced maybe by terrain, maybe by some variations in land cover or surface heating or something like that. And then we have a storm that moves over that. The updraft basically sucks it up and sucks up the rotation, and then causes the tornado to form. All right, so what's the issue? Well, there's a timescale issue. So again, kind of digging back into 40 years in history and kind of moving through the early 2000s, observations have historically taken a long time to obtain. So they've been inadequate in identifying and isolating some of these really rapid scale processes that are occurring. So as just a little sort of eye candy and motivation, this paneled figure over here on the right-hand side is the formation of a tornado. And if you notice the top numbers here, these are the timestamps. So 2051:00 is the seconds, and 16 seconds later, this is how things are looking. You can see we have basically a low-hanging wall cloud. We have what appears to be perhaps rain, maybe a little bit of dust swirling around. We do have a funnel cloud that we can see here. And at this point in time, our funnel cloud is actually in contact with the surface. So between this point and this point, there's only 18 seconds that have elapsed. And then moving on from that, if we jump a little bit into time, by this last picture here, so 2055:10, we have a very large wedge tornado on the ground. And so just as a little point out here, this is 4 minutes and 10 seconds between no condensation funnel whatsoever and an extremely large and violent tornado at this point. So obviously things are happening very quickly. And this also serendipitously represents the volume scan time of a single volume of WSR 88D data coverage. So one 88D volume scan is going to encapsulate all of this happening at one time. So you can see the problem here. We're in no way actually representing the rapid temporal evolution of this scenario here. So we need to sample more frequently, and we also need to get closer to the ground. So we know this is a problem with tornadoes and with 88D data, the 88Ds being stationary. Tornadoes are who knows where in context with the location of the 88D. We want to see closer to the ground. This even is problematic with mobile radars. Because certain mobile radars, in fact, most of the time mobile radars are not deploying immediately within, a mile or so of a tornado. So we still have issues getting very close to the ground, like getting the lowest 100 meters or so of the ground. All right, so enter RAXPOL here. RAXPOL is a mobile Doppler radar that is very rapid scanning. So formally, it's an acronym for the Rapid X-band Polarimetric Mobile Doppler Radar. So this is a picture of the radar right here, actually deployed on the May 31st, 2013 El Reno tornado. And this is a sort of nicer background with the radar. So this antenna spins around at a whopping it completes one full 360-degree scan every 2 seconds. So the thing moves really quickly. And as a result of that, we can actually acquire data very quickly, and it samples in a way that's actually quite different from what an 88D samples. I'm not going to talk about the technical aspects of this, but if you're interested, feel free to ask, or we can talk about it offline. So 360 degrees in 2 seconds implies that it can complete a roughly 10 degree elevation volume in about 22 seconds. So we're basically consolidating our temporal updates very substantially. We can acquire a lot of these in the time that it takes a WSR 88D. Okay, so in light of some of these newer observations, and by the way, I should backtrack a little bit. I'm not really talking about other sources here, but there are and have been recent modeling-based sources that have also been investigating this time height evolution. So we want to compare what observations are seeing, what the models are seeing, and put together a nice coherent picture of tornadogenesis, utilizing the best of both of these representations of this process. So using these rapid scan data, we're trying to answer the questions of, does a tornado form from the top down, bottom up, or something else? So essentially, this is boiling down to what is the time height evolution of rotation as our tornado is forming. So a little bit of past work for my PhD and for my colleague Mike French's PhD. We together looked at several rapid scan cases. Mike used a different instrument, but we collectively looked at 4 cases. And in those 4 cases, we did not find any evidence of top-down rotation. So just a little picture over here on the right-hand side. This is illustrating a constant pseudovorticity contour, which was 0.2 rotations per second. And every block here represents a time spacing, delta t, of 17 seconds. So every 17 seconds, we're getting new information. So we see that the strongest rotation actually starts close to the ground, and it almost kind of pulses upward a little bit. And then all of a sudden, within 60 seconds of the original tornadic rotation, we have a coherent vortex from the ground up until roughly about 3 kilometers or so. However, we do need better spatial resolution. The instrument that Mike was using was a little bit coarse in azimuthal resolution. And we also are missing near ground data. So near ground being at heights below about 300 meters above ground level. So that's what this study is really aiming to investigate. And we also want to add cases here. Obviously, tornadoes are hard to sample. And because they're hard to sample, it's very difficult to get a statistically robust sample size. And I'm not claiming to have that achieved already, but we're at least adding numbers to this. So what did I do? Basically, manually identified and tracked tornadic vortex signatures from RAXPOL, looking at all of the elevation angles that we had data for. and doing this consecutively with time. And actually what I did was I found what I would consider to be a very nice vertically continuous vortex. And also when that vortex kind of was in the same temporal time frame as what the National Weather Service damage surveys confirmed Genesis time was. And then I worked backwards and tracked these different tornadic vortex signatures backwards with time until I couldn't see them anymore. So the criteria of a tornado, there's a little bit of detail here, but roughly I looked at changes in radial velocity that were greater than 40 meters per second or so over a distance of less than 1 kilometer. So as I mentioned, we need to have more cases. So I'm adding several additional cases, 8 specifically. They're listed right there. I'm not going to go into all these cases individually, but if we get right down to the nuts and bolts of what's happening here, looking at these tornadic vortex signatures with time and height, for our first case, by the way, these red triangles indicate tornadic strength rotation. Blue circles mean that it's almost tornadic strength, but not quite. It's missing probably that delta V greater than 40 meters per second. So some of these are like between 35 and 40 meters per second was the threshold I used for subtornadic. And then X's mean that there either was nothing available, or there either was no data available, or there were it didn't meet the threshold. Okay, so for this first tornado, this is kind of interesting. We see definitely some subtornadic rotation at low levels, but we do see a signal that kind of illustrates maybe a little bit of top-down process going on here. So we see our TVS occurring first between about 2 and 3 kilometers, and then pretty quickly it descends and simultaneously ascends. So this would perhaps argue that something might be happening more similar to a descending process. But look at the time scale here. This is occurring over 1 minute and 20 seconds. So definitely not the traditional temporal scale of your dynamic pipe effect. So we're going to kind of put that one aside and see maybe what's going on with that a little later. Second tornado, this was the same day as the first tornado, same supercell even, but about an hour later. So for this one, we see that strong rotation developed again very near the surface. It kind of we had some instances where it actually was tornadic strength, although there was nothing above that near the lowest elevation angle. So it's debatable about whether or not you actually want to call that a tornado. But in this case, we're definitely seeing a concentration of rotation at near ground levels, and then it builds upwards with time here. But again, notice the time frame. These are very short duration. So this is about, this is less than 2 minutes between seeing tornadic strength rotation at or very close to the ground and a scenario where we have basically a coherent vortex up to at least 1.5 kilometers. Okay, this next case was a case in the Texas Panhandle where the supercell had actually produced a really nice long-lived tornado outside of Pampa, but we weren't there in time. So the radar got there, and then the supercell started to produce these kind of marginal tornadoes that barely met tornadic threshold. But we did see 4 additional. So we started scanning after genesis of the first one, so that one doesn't count. And then we see a little bit of a spin up, but it didn't do anything. And then at this point, by the way, there's a little bit of beam blockage right here. So this white space indicates that we just don't have any data. So our tornado that's forming right here is, again, concentrated in our rotation at the lowest levels. And notice our y-axis is different in all of these cases. Here, we're only going up to 2 kilometers. Here, we're going up to 5 kilometers. Here, we're going up to 2.5. This is a function of the geometry of the radar based off of where we are in comparison to where the tornado was. So in this case, we were actually closer to the tornado. So our upper level scan was actually not particularly high above the ground. But here you can, again, very clearly see that in this situation, you basically have a tornado that's confined to the lowest 750 meters. So this is something I'm not going to address today, but it does raise a little bit of a dynamical question of what's happening here, that we're getting tornado strength rotation that is just so confined in the vertical. Another tornado forms, and again, we can sort of see this bottom-up process here. Third tornado happens right about here. Here, we might have something, again, that's kind of saying we're getting a spin up aloft, but those are not continuous in time, so it's kind of unclear what the function of that was. Perhaps it was actually forcing the air below in and up through that vertical acceleration into that low pressure perturbation aloft. And here we almost have like a simultaneous scenario where the tornadic rotation is converging almost all together instantaneously. And then the last tornado from this case, again, was definitely a bottom-up scenario. But all of these tornadoes are relatively shallow, although I will add that we didn't secure data much above 1.5 kilometers. So it's possible that maybe there was some kind of stable layer here or something like that. Or maybe the vortex was particularly like horizontally tilted or something. So we're not actually seeing a good representation of what's happening with that. Another tornado, this is the infamous El Reno tornado from May 31st of 2013. This looks a little bit different. I forgot to plot the X's on here where we don't have TVSs. But here, very clearly, we go from subtornadic rotation to tornadic rotation at the 0-degree elevation angle. And then, boom, all of a sudden, we have this vertically continuous vortex. And the time frame here, we start having our first TVS at the ground alone, and then within about 2.5 minutes, so this is about 2.5 minutes, till we get a fully developed tornado. And then this last case here is, much of the same. We, in this scenario, kind of have like a simultaneous, go from very kind of weaker, broad rotation in this case. There was rotation present, but it was just quite broad. And so we go from this broad rotation to a TVS that's concentrated within roughly the lowest 1.5 kilometers. And then that kind of holds up for roughly 3 minutes or so until the deeper, maybe even longer, 3 to 4 minutes, until the deeper tornado develops further down the road. Okay. However, I do want to point out that tracking the TVS itself can be a little bit problematic because there is a little bit of a degree of subjectivity in here. We don't necessarily have a consistent definition for what gate-to-gate velocities should look like. For example, is the threshold 40 meters per second over a distance of less than 2 kilometers? If you apply that, sometimes you get larger scale tornado rotation or larger scale rotation than what the tornado actually is. So there's some problems. So I also wanted to do a little bit of sensitivity testing, and I did this with that very first case where I said, well, maybe there's a little bit of a signal for top-down process occurring. So here, what I did was I ubiquitously just defined a TVS based only on the delta V value of either 40 meters per second, 30 meters per second, or 35 meters per second. Sorry, 40, 35, or 30 meters per second. And they all had to be at distances less than 2 kilometers. So I broadened things out a little bit. And I did this because this is sort of the classic definition of what makes a tornado in mobile radar data. So doing this, at 40 meters per second, we get kind of, and by the way, this plot looks a little bit different than the one I showed here because the criteria were slightly different. And I said there's a little bit of detail in what I did initially for the publication, and then going back and redoing things. So I actually widened the radius to 2 kilometers. It was actually 1 kilometer before, and there were some other little details. Interestingly, in the 40 meters per second case, we have strong rotation at mid levels, and then it kind of breaks. And then we go, so we have a sweep where there's nothing, there's no tornadic rotation anywhere. And then all of a sudden, boom, we have a tornado everywhere from roughly, 300 meters above ground level to all the way up through about 4.5 kilometers above ground. So this is kind of interesting. So right here, this actually gives us a different interpretation in the time height sense compared to what we just previously looked at. If we reduce that to 35 meters per second, here we get a little bit more of the sort of top-down kind of scenario. But again, we also have that missing sweep where we actually don't have anything that's conforming to a TVS there. But we can see a little bit better, perhaps, this descending scenario. But if we reduce it even further to 30 meters per second, then we go and we basically have strong rotation, tornadic strength rotation everywhere aloft above about 2 kilometers, but our tornado actually kind of shows up everywhere. Now it is showing up a little bit earlier than what that blue line is. So that blue line was the damage survey from the NWS. So we could perhaps argue that maybe this is subtornadic and we're not actually getting a tornado at this point. But the point is that defining a tornado and identifying the time height evolution based only upon the TVS might be a little bit problematic, because there's a degree of subjectivity involved here. So if we look at another parameter here, we just are looking at the delta V. So not having any kind of spatial threshold, we're only looking at the strongest delta V values across the board. In these cases, we actually see for the case we were just looking at, you can definitely see that strong rotation concentrated above 2 kilometers or so. But we do see a very nice signal for a blurb of very strong delta V's right at the time that NWS has the tornadogenesis time. And then, and so we don't really see as much of that descending trend based upon the values of our delta V. Perhaps, a little bit later on, but we have a tornado already kind of occurring at this point. For our second tornado, we can see something kind of interesting descending there, and maybe that's acting to advect some vorticity towards the ground. The tornado start time is again in that black line, and here we can see again our strongest rotation starting at the ground and then developing upward with time. For that interesting scenario where we have multiple cyclic tornadoes occurring that are relatively shallow and weak, almost everywhere we're getting just concentrated vortices in the vertical. There's no descending or ascending signals occurring here. All right, May 31st, so this was El Reno. This is kind of interesting. There was a lot going on in this case, and sometimes the area of rotation was actually not the same physical location where the tornado was. But we do see that we have a strengthening low-level mesocyclone, low to mid-level mesocyclone, probably strengthening low-level mesocyclone right about here. And then formal tornadogenesis time was right here. So we can see that, again, we're kind of having maybe a little bit of an intensification going on here. But if we look really closely within the previous 2 volumes, we do get a non-descending scenario going on, or a bottom-up scenario. And then the last tornado that we see, again, was kind of everything converging all together all at once. Although, again, you do see a really nice signal for a strong low-level mesocyclone. And that's a very important point to make here, is that all of these tornadoes did require a moderately strong low-level meso. And that makes sense because that's really what's driving that upward directed pressure perturbation acceleration into the low, which is going to force that rotation near the surface to converge together and to amplify to tornadic rotation strength. So there is an important element that is being contributed from that low-level meso in this process. And then if we look at pseudovorticity, which is basically looking at those maximum delta V's that I showed you before and dividing it by the distance between the values there, we come up with a very similar scenario where basically we don't see really much evidence for descending tornadogenesis anywhere, and everything's pretty much happening quite similarly over time and height here. So almost like kind of that simultaneously convergence scenario going on here. Okay, so in summary here, I put together basically a bunch of cases all of the cases really that we have data for so far, the 8 that I showed here, and then a couple additional ones. And basically saw that if we look at the percentage of cases where there's a TVS present with time and with height, so prior to tornadogenesis occurring roughly, it's actually technically roughly about here, we can see most tornadoes are developing near ground rotation first, but we do see sort of a secondary signal for something happening at about, that low-level mesocyclone height. So most of the parameters that we looked at are suggesting we have rapid intensification, mostly from a non-descending process. And this is occurring through heights of, several hundred meters above ground to about 2.5 kilometers or so. And it's really important to note that tornadogenesis is an incredibly rapid process. So the idea of this top-down scenario is probably our eyes deceiving us. Yeah, if we look at this picture here, we have a nice little bowl-shaped wall cloud, and you wouldn't necessarily look at that and think there's a tornado, and yet we do see ground-based debris. So our eyes are not necessarily telling us the true story. All right, so now I'm going to throw in an additional sort of philosophical question here. So what is a tornado? Of course, by definition, we know that a tornado is some kind of really rapidly rotating column of air. It's touching the ground. It's extending upwards into the cloud. But how fast do we have to consider this rotation to be tornadic? And typically the threshold is, you know, it's got to be rotating fast enough to be inducing EF0 damage at the ground. All right. But, you know, how do we define this, especially in the context of radar observations when we are not usually seeing what's happening immediately at the ground? Another contribution to the definition of a tornado is the presence, or perhaps not, of a funnel cloud. So a funnel cloud is not required, although it is helpful, but we need to see ground-based debris or dust circulating. So it may or may not have a funnel cloud, but we have to have that ground level rotation sufficient of inducing EF0 damage. So most tornadoes have a diameter of 2 kilometers or less. And as I alluded to earlier, most of the time we create this threshold of this delta V greater than 40 meters per second. And that's within roughly about 200 meters or so of the ground. Okay, so another problem that we have is that radars actually typically suck at detecting tornadoes as they form, especially if we are taking out the 88D, or sorry, taking out the mobile radars and only using 88Ds. So if we look at our coverage, you guys are probably all familiar with this, but as we go away from the radar, the distance increase will actually degrade the azimuthal resolution of our data. And also with distance and with that degradation of azimuthal resolution, we're going to negatively bias our maximum wind. So we're basically averaging together a whole lot more air that's rotating. Some of it's rotating very quickly, but some of it's rotating not so quickly. And we're averaging all of that together. So we're going to create a low bias to our radial velocity estimates. So the further the distance we are from the radar, the higher the beam is as well. So we're going to miss near ground signals. And obviously what I was basically just arguing is that we tend to have very strong rotation at or near the ground, either as a predecessor or as a good signal that tornadogenesis is occurring. Furthermore, we have these radar-based observations of tornadoes that are inconsistent with their definitions. So I alluded to this before. Here are 5 different studies that use 5 different thresholds using 5 different instruments of what makes a tornado in their data sets. So obviously the 88Ds are potentially problematic here. So over here on the right-hand side, I have an image that is close to home for me. So this is Athens, Ohio. I live roughly right about in here. We had an interesting scenario where we had a pseudo supercell move through here. I say pseudo because the meso was not particularly persistent with time. And within, you know, roughly 15 seconds of this particular image sequence here, which, by the way, you know, you look at that reflectivity image and you don't get red flags thinking, oh, this is going to be producing a tornado. You look at the velocity signal and you can see a little bit of motion towards, a little bit of motion away, same over here, a little bit of motion towards. So we do have some rotation that's happening here. And yet at almost immediately, we have this happening. So it's tricky to use radar observations to confirm tornadoes. All right, so here's a question for you. This is a mobile radar image, reflectivity, upper left, correlation coefficient, ZDR, and Doppler velocities here. So my question to you is, you know, is this a tornado? I would look at this and I would say yes. I see a nice signal for outbounds, inbounds, pretty strong looking. If you look at the color image here, we would say probably at least a delta V of maybe 35 meters per second or so. We don't know what the grays are. They actually exceed the color table here. We have a tornadic debris signature in our rho HV field. So we have evidence of lofted debris. And this is what we see at the ground visually. So our eyes looking at this would not say there's a tornado happening. And yet we have evidence of lofted debris and a very strong couplet. So I'm illustrating here this disconnect between what our brains are processing and what's actually happening in the radar data with the actual air, or what we're sort of, it's really hydrometeors that we're looking at, obviously, but what the hydrometeors are telling us about the nature of this rotation here. Okay, so here is another scenario. All right, we have, again, a situation, reflectivity here, correlation coefficient, velocities down here. Velocities are rather weak, but we do have some evidence of perhaps a little TDS here, and we have a little bit of evidence of a weak echo hole. And this is what is being seen. So again, you know, this is obviously a weak tornado based on these velocities, but we can sort of get at the idea that there is a tornado, especially with these TDSs. So again, kind of like a little bit of hesitation here. If I were looking at this velocity signal, I might be kind of hesitant to say, I don't know, like, I feel like that might not be quite a tornado. And yet we are seeing some evidence of lofted degree. This is where these dual pole parameters are particularly useful. And by the way, the beam height on this is about 220 meters above ground level. Okay, so why is it so hard to change our perspective? I hope you're understanding right now that it's unlikely that this top-down process is actually happening. And if it is happening, it's happening on timescales much more rapid than what we have originally and historically attributed this descending process to. So I think our perspective is based on what those visual cues are, what we are seeing with our eyes, with the funnel cloud in particular. We kind of attribute a tornado to the funnel cloud, whether we like it or not, whether it's part of the formal definition or not. But it's really important to note that the funnel cloud does not directly imply that we have ground-based rotation. We can have funnels, as we all know, that don't have ground-based rotation, and simultaneously, or not necessarily simultaneously, but similarly, we can have tornadoes without funnel clouds. So let's take a minute to talk about the funnel cloud itself. So the funnel cloud is, the idea of the behavior of this funnel cloud is going to be attributed to a couple of scientific principles that we all know, we all are comfortable with. Obviously, the environmental lapse rate is going to cool as we go up. So, or the environmental lapse rate implies temperatures cool as we go up. So as if air is cooling as we go away from the surface, if we have air that's ascending and is also simultaneously adiabatically cooling, it is going to become more saturated as it rises. Clouds are going to form when we have air that's saturated. And here's a little bit of science that is specific to this funnel cloud tornado scenario. Decreased pressure reduces the saturation mixing ratio. So if we are at a lower pressure, we can actually achieve condensation more readily than we can given the same amount of water vapor in the air at a higher pressure. And we also know that rotation is going to dynamically decrease our pressure. So if we put all of this together, the formation of our funnel cloud is basically a function of the thermodynamic profile below the LCL height. So what is the temperature doing with height? What is the moisture doing with height? Let's hypothetically consider a situation where we have cloud base here. So here's our cloud, here's the ground. We have an area that is equally rotating, exactly the same everywhere. All right. So given this scenario, we might first start to see a little bit of a decrease in our cloud base at the top here. Reminding you, rotation is the same everywhere. That rotation is inducing slightly lower pressure, which is allowing our cloud to form at a slightly lower height here. Okay. As we strengthen this rotation and it becomes stronger, now we can cause condensation to happen at a progressively lower level. And if we intensify it even more, it's even lower, etc. So the process of forming the funnel cloud will always be a top-down process. But we might have tornadic strength rotation from the get-go here, and our condensation funnel just isn't already at the ground, especially if we have a relatively dry column of air between the cloud base and the surface. We might have a scenario where we have tornado strength rotation without any funnel cloud whatsoever. All right, so quoting my good friend, good old Austin Powers, what does it all mean? All right, so now putting the forecaster hat on here, operational tornado warning issuance is hard. And I applaud you all for having to do this job because it is not a place where I would particularly want to be. We know that tornadoes form quickly. We also know that basically the best predictant is going to be the presence of this ground-based rotation, which is basically unobservable. We don't have nearly sufficient like mesonet surface observations. Our radar observations are essentially useless at the ground unless you just happen to luck out and have a mobile radar in really close proximity to where a tornado is forming. Furthermore, the radar observations themselves are going to be inconsistent in terms of quantifying what makes a tornado. And then let's throw in another layer here, and you all are on the East Coast. East Coast tornadoes are especially hard because they're commonly associated with QLCSs, which, by the way, I haven't even talked about here. I've just been talking about supercell tornadoes and tornadoes that form from mesocyclones. QLCS tornadoes form in sometimes similar manners, but also in, very quickly, oftentimes from the ground up as well. And these processes are oftentimes exacerbated, and problems are exacerbated in QLCS scenarios as well. But even that, we oftentimes have like these weird amorphous or atypical supercell patterns, like the example I showed you that was kind of close to home for me. So we don't have classic hook echoes. All right, so real quick, find the tornado here. And by the way, you already have negative lead time. So we have reflectivity, velocity, rotation, correlation. I'll give you a second to look at that. So where is the tornado? Well, it's actually right here. So that tornado did end up verifying as an EF1 at this exact time. So again, issuing a tornado warning on that is very tricky. So what are some implications here? Even if we could observe with 100% fidelity the rotation associated with developing tornadoes, it would not ultimately improve our lead time because we just don't have enough time between when this rotation is present and when the tornado actually is forming. So if we continue under our current model, we will never achieve this 100% accuracy. So warning strategies, obviously situational awareness is very important. So also warning on a strengthening low-level mesocyclone is a really good strategy as well, but it's not necessarily a guarantee. And sometimes we are forced to warn on reports, which is implying negative lead time, which nobody really wants. Stepping back, this is a really cool survey or study. I'm just going to allude to it quickly, but if you have the opportunity to read this, this is Bentley et al. 2021 that looked at tornado warnings and verifications of tornado warnings and basically determined that radar-based warnings still have the best probabilities in terms of false or the lowest false alarm rates. So radars actually are better than trained spotters, better than observations and reports. And then notice here our worst false alarm is associated with emergency management, law enforcement. So sheriff NATOs are a thing, unfortunately. And for anybody who's done any kind of storm chasing, we'll see tornado reports and we'll be like, really? I'm looking right at what you think is a tornado, and this is not a tornado. Kind of a little source for chuckles. And also, if we look at missed events that end up being verified, what those verifications were, still, train spotters were good. I missed somewhere in here, I thought there was a radar-based thing. I might not have grabbed it. But basically, the idea is that radars are still our best bet, despite the problems. But what can we do in the future? Because we know radars are problematic. So the best bet here is going to be to basically combine our observations with really high resolution, short-term cams. So we need these convective allowing models to inform our warning strategies by looking at where the cams are having storms initiate, looking at how they are progressing the storms, and using probabilistic guidance through a whole bunch of model runs to determine where the best probability for rotation is. So Warn on Forecast is a really, really great tool, and it's unfortunately not 100% operational. In fact, it usually operates only mostly in the spring or potentially high-end events. But this Warn on Forecast generates these probabilities of likelihoods of certain storm attributes, like where is hail going to be maximized, for example. or what's the probability of hail exceeding 1 inch across all of the different various model ensemble members, etc. Okay, so we're running running low on time here. I say, why do we still say tornadoes touch down? This gives me nightmares. So please, NWS folks, let's really try to get away from this lingo because it's not scientifically accurate. Similarly, tornado on the ground, by definition, a tornado is already on the ground. So let's try not to say that. So what can we say? Just simply say a tornado occurred or was observed or formed. All right, so I will end there. I'm going to exit my my PowerPoint mode here and go back to my screen where I can see you.
All right, Jana, thank you so much. There's so much to unpack. Also, hopefully everyone can hear me. I had some internet issues, so hopefully everyone can hear me. Good, glad to hear. Perfect. I had a couple of questions, comments of my own, but I was going to first open it up to everyone. We did have people well beyond Eastern Region, so thank you to everyone across NWS who tuned in to this for this morning. I do see a comment. So I guess the question is, interested in the opposite side of this topic with the number of null events that have TVS level rotation at 1 kilometer or higher, but do not produce the low TVS on it. If you have any thoughts on the number of null events despite a decent low-level cyclone, mesocyclone being present.
Yeah, this is a very good question. It's unfortunately a lot harder to identify these null cases than it is to identify the successful cases, because it's kind of like a fishing expedition. Or, you know, I guess we could potentially use like spotter net or something like that, where we're getting funnel cloud reports. That would probably be the best way of identifying those. But yeah, I mean, you do definitely have scenarios where, and I think anybody who's ever chased has seen a funnel cloud without it actually producing ground-based rotation. I've looked at probably 2 or 3 of these scenarios myself, because I was physically there. I saw the funnel cloud. I know that we had radar data, and yet it didn't actually produce a storm report. So what I can say is that the ground-based rotation just isn't there. And obviously, I think that makes sense. You know, if you have a strengthening, for whatever reason, you're kind of concentrating rotation aloft. Oftentimes it's with some kind of like RFD cut or something like that. And you have a mechanism for kind of doing a little bit of a spin up at the low level mesocyclone, or so that happens. But for whatever reason, you are not spatially consistent with or temporally consistent with near ground based rotation, you're not going to get a funnel or an actual tornado. But in terms of like a larger scale statistical representation of when and how often this happens, I have no idea. I would say I wouldn't. I don't know. I don't even feel comfortable kind of saying a probability, but it definitely happens. Yeah, that's all I've got to say about that.
All right. Well, thank you, Jana, for the input on that. Kudos for your presentation from Matt Bunkers out in Central Region. So thank you. I got a question. John, please go ahead.
Hi, good morning. Thank you so much for your talk, Dr. Houser. It was awesome. And thanks from Central Region to the Eastern Region folks for sharing this with us. Just kind of want your comment on, you know, so what we see in the 88D is in a typical velocity scan is really just an amalgamation of trajectories originating from different sources. So one of the things that's still kind of taught in basic radar training is just to look for this magical rotational couplet that exists, which we all know and your research suggests doesn't just, you know, happen that way. So one of the things, you know, a few of us have started to look at are, you know, indications of flow regions in a supercell, for example, maybe along the left flank convergent boundary that may originate and maybe more closely feed the tornado seed. Now, we know that the 88D is not really research grade, and we also know that this, you know, you can't really see much below a kilometer. If you're not seeing anything below a kilometer, you can't use that theory anyway. So anyway, just kind of wanted your comments on that.
Yeah, I mean, 88Ds are what we have to work with, right? So we kind of have to force ourselves to try to look for these kinds of signals. And yeah, I mean, the forward flank convergence zone, or, you know, the streamized vorticity current, however you sort of want to, you know, look at this, definitely is something that is at least contributing to tornadogenesis probabilities. And the likelihood, in my personal opinion of that, is that it strengthens the low-level mesocyclone. So if you have strong baroclinic generation of vorticity along that forward flank, and we can see that perhaps kind of as a manifestation of this forward flank convergence zone or the streamwise vorticity current, most of the vorticity in that is not, at least based on like Lee Orff's simulations, and he's kind of the proprietor of this idea, most of the vorticity is actually not making it into the tornado, but rather the vorticity in the tornado is coming from, in his simulations, is coming from these like very small scale spin-ups that are generated along the forward flank boundary there, and perhaps even along the rear flank boundary, and they kind of amalgamate. And, you know, so seeing ever observing processes like that, even I think with mobile radars, it's going to be very challenging. So this is where we really need to just ultimately change the paradigm and really just kind of say, all right, we're using radar, but we're using radar in conjunction with these WARN forecast and cams, and looking at, you know, where are the cams suggesting that rotation is going to be developing in an hour. Let's make sure if we have a storm that's kind of in the same ballpark, we might want to give this storm extra special attention and kind of move forward looking with that in mind.
Thank you.
Thank you, John, for the question, and to you, Dr. Houser, for that. So if there are no other questions, I had a comment of my own. You brought up the importance of course, look, we are where we are. We have the limitations that we do that exist, as you highlighted perfectly in your thoughts this morning. But one thing that's important to enforce is that mesoanalysis component and the situational awareness, because that changes the game. Because if you're able to heighten your awareness situationally, of course, we already do this to some extent for sure. And we have regional efforts that are also supporting this exact point and this exact issue. But to continue doing that also locally as these situations present themselves allows us to, as you put it this morning, hone in on these scenarios and be able to lock in ever more precisely into where the threats are, rather than saying, oh, our whole CWA, and that may be the case in some situations. But for those that are not those situations, that's where this can also be a highlighted point. So I just really wanted to reinforce that. I also didn't want to forget, Jeff at the top linked the Bentley paper you referenced at the very top of the chat for everyone. It's a very good paper as far as the insights to the different sources of consideration for analyzing tornado verification.
And that's what I was just going to say too. In that Bentley paper, they basically are saying if you combine the situational awareness, and if you look for STP that's greater than 0, and you couple that with instances where you're seeing rotation in storms, you have a much higher probability of verifying in your warnings.
Exactly. Couldn't have said it better. And then you're getting some more kudos from other folks across the agency. It sounds like there's some interest in seeing QLCS data on this from someone who's also a Buckeye. So thank you, Desiree, for that comment. And for the rest of the kudos, are there any other questions from folks in the field? Feel free. I have a few minutes, for sure.
I will comment real quick about the QLCS, and that this is a really good point. QLCSs are just so hard because they're poorly observed. It's almost impossible, unless you're serendipitously in the right place at the right time, to get good mobile radar data from these. There are a couple of like Vortex Southeast cases or now Vortex USA cases that are pseudo okay, but they're so fast moving. They're quick to form. They're quick to dissipate. It is really hard. So we're left with basically using 88D data that has 4-minute temporal resolution, which is not going to really do what we need it to do.
Really good points. Jeff, you came on. Did you want to add something from your end?
No, I just I actually got bounced out. I think we had a network hiccup, so it just came back and my camera was on.
Okay. Well, hopefully.
Matt's got a question here. I see Matt.
Yeah, hopefully, if that network thing affected the recording, we'll find out. So hopefully it didn't. But Matt, did you have a question?
Yeah, Jana, in some of your images when you were looking at the delta V, it did, indicate at the lower thresholds you had a mid-level mesocyclone well before. So it seems to me that at least offers some, I guess, probabilistic potential of there being a tornado. Have you looked at that enough to know if there are cases where that really doesn't show up until right about the tornado? Or I'm just curious. Obviously, there's other things we can take into account, but farther from the radar where we can't see the low levels, that's still perhaps the best bet along with the environment and so forth.
Yeah, absolutely. And yeah, I mean, you're going to generally have a better likelihood and probability for tornadoes, especially, tornadoes of substance, so to speak, these EF2 or greater tornadoes, if you have a more robust supercell to begin with. The low level meso, I think, is really the key. So if we're seeing a pretty strong rotation at the lowest elevation angle, which is hopefully maybe like 1 to 1.5 kilometers above ground level, and especially if you're seeing that kind of ramp up, that's definitely a good indication. I have not looked at loads and loads and loads of these things, but I will say I had a student who did a comparison in low level and mid level mesocyclone size and intensity in tornadic versus non-tornadic cases, and we definitely found a statistically robust, I'm not going to call it significant, but robust signal to emphasize again this point that if you have a low level mesocyclone, the stronger the low level mesocyclone is, the more likely you are for tornadogenesis to occur. Mid level mesocyclone was sort of secondary to that, but yeah.
Thanks.
All right. Thank you all for the really good questions and discussion. Another comment. Yep. The challenges of the 88-day limitations, for sure. Acknowledging that point. Which is where the question of what the future of the radar network will look like comes into place. And those are questions and conversations that are ongoing for sure. So that being said, are there any further questions or comments?
Yeah, so John, you're right about the dual pole information and the fact that that can also be important to consider. And we can also gain, there is some evidence to suggest that if we're looking at ZDR, for example, and we do like a cross-section of ZDR to take a look at proxy updraft temporal time series, for example, if we see these updraft pulses and we have like a higher extension of stronger upward motion, that could potentially also indicate, a scenario that's more favorable for tornadogenesis.
Really, really good points being brought up. And more importantly, I just want to remind everyone, we are coming up to the top of the hour, but I do want to remind everyone this webinar has been recorded. So we, minus any glitches here at ERH with the internet this morning, we should be good with the recording on Google. So we'll get that up, of course, along with the slides, as long as we can get them up as well. And with the permission to have them up as well. So that sounds like we just got it.
Works for me.
Sounds good. I guess I'll offer up if there are any final questions. A lot of the other questions I had, people already asked. So any final thoughts from anyone across the field? Okay, I see a virtual applause. So I'll join in without sending an emoji. Thank you so much. Really, just a lot to unpack. And I think this is going to be a great training point too for folks as well. And really appreciate your time this morning, Jana, and thank you so much, because there's a lot of long stem traditions and thoughts that take time to process and how we want to change them, and presenting it this way was great. So thank you for that.
Absolutely.
And thank you all to all of you for attending this morning. Again, as I mentioned, this will get uploaded to our Eastern Region Science Training webinar page so as soon as we get it available. So thank you all, and wishing you all a great rest of your Wednesday.
All right, everybody, take care. Thank you.
Thank you.